Hello, and welcome to video number 10. It's a topic that's dear to my heart. I've worked on it for many, many years. It's irrigation system uniformity and efficiency, brought to you by Cal Poly ITRC and the CDFA FREP program. As a reminder, the Fertigation book in English and Spanish, Drip Micro book, and numerous other resources are available on the ITRC website. One of the things in particular is the series that we have, the fertigation video series that we have that are used to demonstrate lab exercises as opposed to just the lecture format. Now, here's the general idea. You know, the whole deal on fertigation is interesting if you consider fertilizers, interactions, nitrogen cycle, you know, the gizmos that we use to inject fertilizers, the sensors, all that sort of stuff. It's very interesting. But here's the bottom line. The bottom line is that the efficiency and uniformity of your fertigation application is only as good as the efficiency and uniformity of your irrigation water application. And we have two concepts, and I've used the words, but you really want to pay attention to this. Two interrelated but different concepts. One is uniformity, and we usually call that distribution uniformity, or DU. And there are technical descriptions as whether it's a DU of the low quarter and so on, but this concept of uniformity. The second one is efficiency, and these are different, and I hear people getting mixed up with these very, very frequently. First, concept of DU, distribution uniformity. This is what our Cal Poly San Luis Obispo student team's been measuring for many, many years, decades actually, every summer, and what the mobile labs in California measure. They don't measure efficiency, they measure uniformity. So what is uniformity? It's a measure of how evenly water is applied to plants throughout a field. Not to the soil, but to the plants. For example, you can have big bare spots on a drip system, you know, where there are large areas of the soil that get no water at all, and it's not very important if that's for trees. On the other hand, if you're growing corn, you want every spot wet because there's a plant at every spot. So the idea is plants here. The second thing is in terms of the values. When you look at the values that we have, they are numbers like 1 is the maximum number you can have. It's not an efficiency. The maximum value of DU is 1. And if you have a DU of 1, that's perfect. In other words, every plant in the whole field receives the same amount of water. Then how bad can you get? About the worst that we see is value of 0.25. And this may not make sense here, but what it boils down to is it's really bad, and some plants get about 8 times as much water as other plants. So that's really the pits. Here's a graphic in which we attempt to explain the concept of uniformity. It's sort of a slice through the field. Slice through the field, if you can measure the inches of water, so this is the depth of water that goes in at various parts to plants throughout the field. And so you have, if you notice, there are different amounts of water that go in at different places. And the concept of DU is the same whether it's a surface irrigation for furrows or border strip or pivots or hand move sprinklers or drip micro. The concept is the same. Do plants all get the same amount of water? And of course they don't. And so how even is it? And then, by the way, how do you measure the uniformity? It's impossible to apply water perfectly evenly, but we try to get pretty good. Now, our teams from Cal Poly have gone out for years and years, as I mentioned, and evaluated drip microsystems primarily. Why not sprinklers? Why not furrows? Well, quite frankly, there isn't a lot of interest in furrows. This doesn't mean it's not important, but farmers just are not too interested in having their furrow systems evaluated, or sprinkler systems for that matter. In general, the people who seem to be the most interested are the ones with drip micro. So here are the results of hundreds of tests with micro sprayers and drip. And what you see on, let's take a look at the micro sprinklers on the left. The vertical axis is DU, and you see the maximum value is 1 and the lowest value is 0.2. And there's one outlier there around in the year 2010 that's down there about 0.2, maybe, what is it, 0.28, something like that. And the red triangles show you the average uniformities, the average DUs for each year. Then you move over to drip, and you get the same type of thing, and you have a lot of highs and you have some lows. So, but it gives you an idea. There's quite a spread actually in performance. If you sort of use your imagination, it looks like the performance on the average has gone up over the years. The same graphs, and now I want to look at a couple other things. One is that these uniformities, if you look at the high values on drip and microspray, especially the drip, you see a lot of them are right up there near 1. Certainly not all of them, but you know, there's no other irrigation system that gets anywhere close to that, just so you know. But there are some remarkable systems out there. And the average numbers are higher really than what you get. You know, we can talk till we're blue in the face about what's practical or theoretical, but then there's what's actually measured in the field. These are new systems and old systems and everything in between. And these are really good. You will notice, however, that some are really lousy. In other words, an average is just an average. You know, that means they're half of them are higher and half of them are lower. And keep in mind that the reason I'm talking about this right now is that if you apply water with a lousy DU, you also apply your fertilizer with a lousy DU. So what's it mean? Well, before you expect tremendous results from your fertigation program, you really ought to take a look at the distribution uniformity of your irrigation system and try to tighten it up a bit. It's good for water distribution and for fertilizer distribution, and obviously, maybe not obviously, but certainly it is really good for more uniform crop growth. We have short courses every year. They last about a week. We have people from all over come to learn about irrigation system evaluations, and we have software packages for it and some pretty practical training. About 3 days out in the field with drip systems, and then there are 2 days at the beginning dealing with general concepts. And these are usually held every summer, in early summer. With this slide, I'll start to review a few of the simple things you can do that can often make a huge difference in the uniformity of your system. Ideally, what you want out there is you'd like all the emitters to have the same pressure. It's not such a big deal if you have PC or pressure compensating emitters, but if the pressure gets too low, they no longer work as pressure regulators, or their function as pressure regulation doesn't really work. And one of the biggest causes, believe it or not, of strange, uneven, and very low pressures is these hose screen washers get dirty. These are the little devices that are at the head of every hose in an above ground system. You don't see them so much in, or actually you rarely see them in tape systems, but they're common in microspray and emitters above ground for trees and vines. So what do? This picture obviously is of a plugged hose screen washer. You either remove them and put in a regular washer, or you clean them out. And a lot of people just remove them because they're more problem often than helpful. And they were originally intended, when we first started with drip, we put these in because we thought, well, the PVC pipe might break, sand gets in the line, goes down the hose, and you know, it might fill up the hose. What I've noticed over the years is, yeah, that could happen, but this is a huge problem. Just this is more of a problem than it is of value in my mind. There are always exceptions, but it's a major problem keeping them clean. Next one, flush the hose ends frequently. That means you have to have some kind of a gizmo like a figure 8 down at the ends where you can actually access them and flush them. These slides are not fake. These images are not fake. These are real observations that our teams have seen out in the field. Obviously, these hoses weren't being flush very often. How's that? Next thing, which we've known for years and years, is that bacteria grow in hoses. It's not algae, which requires sunlight, it's bacteria. And you have to kill the stuff, you know. And we also have some, well, they're bacteria of all types. You know, there's iron bacteria, there's just regular slimy bacteria. So the tried and true technique for many, many years is chlorine, and that's seen in the upper left-hand photo. There's a little cover over a large chlorine tank. It's automatic. You know, the irrigation system comes on, it starts to put in chlorine. And that type of system puts in a continuous rate. The blue tank on the upper right with a small injector is typical of polymers that people will put in. Primarily, the polymers are primarily put in when you have problems with high calcium or magnesium, something like that, or iron problems where they're mineral problems, and they help prevent precipitation. And then on the bottom center, that's SO2 generator, and we have a whole video on that. Those can be used in organic systems, and they make a sulfurous acid, and the sulfurous acid helps keep the hoses clean. So there are a variety of things. By the way, you wouldn't put chlorine and sulfurous acid in at the same time because they counteract each other. But there are a wide variety of chemicals that you use. And so how much do you use? Oh, that's a tough one when you're looking at bacteria because you don't quite know. I'd say go as low as you can and go to the end of the hoses, see if you have slime there, look at hose screen washers, see what's growing there, and go with as low a rate as you can. Sometimes you have to do it continuously, sometimes just occasional injection works fine. It depends on your water quality. Another one, as I mentioned, deals with the uniformity of pressure throughout your field with microsprayers. Most microsprayers, they are not pressure compensated, and micro sprinklers. And it's pretty simple. If you have a higher pressure, you get more flow out of one. And so if you have high and low pressures throughout a field, you have high and low flow rates. That's called non-uniformity. It's the same way with a lot of emitters. So most of the systems nowadays do not have preset pressure regulators. They have adjustable regulators, and the most common configuration is what you see here, where you have block valves. And they may be automated for on-off, or they may be automated for pressure regulation, or both. But here's what you do. You have to go out there and check that they're set properly. It's unbelievable how often they're not. Sort of in a nutshell, what you do, and we have a very formal procedure, by the way, but if you just want to get the general idea of what you do here, the image on the left shows someone has a pressure gauge with an end on it that has it's a special connection. It's called a pitot tube. You punch a hole in the hose, you put the pitot tube in there, and you measure the pressure. And you do that in a variety of places throughout the field. That's fairly straightforward. You know, usually the beginning of the hoses, the ends of the hoses, you know, one corner of the field, another corner of the field to get an idea. And that would give you an idea. Mathematically, it doesn't give you much, but our procedures that we have, our software actually calculates the non-uniformity due to pressure differences. But just by taking pressures, you get an idea. On the upper right-hand side, you see that happens to be tomatoes there, processing tomatoes, and sure enough, you have to dig up the crazy tomatoes if you want to measure flow rates on tape that's buried. But you see the little cans there. What you do is you expose the tape, or you know, if you have above ground hose, it's already that way, and you put a can underneath every emitter. And there's a process. Normally you put one can under an emitter, and then 30 seconds later you put a can under the next one, and then 30 seconds later a can under the next one, or something like that. You go on down, come back to the head. After 20 minutes you take the cans out one at a time every 30 seconds, or whatever your interval is. and then you measure how much water is in each can. Now that's a very localized thing, but see, all of these emitters have the same pressure. So if you have differences in flow rate, that's usually due to manufacturing variability, which is no longer a huge thing, or it's due to emitter wear or emitter plugging. So it's different than the pressure measurement. This is due to like I say, types of plugging, and maybe it's root intrusion, who knows. Of course, the next thing is you have to cut apart the emitters that are plugged, and you have to actually expose the pathway. You don't just cut the hose, because that doesn't show you anything. You have to kind of whittle away at the emitter itself until you can see the path, and then you look in there. Sometimes, you believe it or not, you have to use a magnifying glass, and for example, roots may be hard to see at first, but then you can see, okay, what is it? What type of contaminant? Is it sand that came in from outside? Is it roots growing in from outside, or is it something that came in from the inside of the hose? So bottom line is you have to get out there and do some digging around. So the pictures up in the top center are pictures of problems found in emitters, things that showed up. Of course, another thing is to check the filters. Now, you might have a hard time believing this, but with the system shut off and with it depressurized, make sure you do those two things. They're different. It's not a bad idea to check the sand in these media tanks. You'll, again, it's kind of hard to believe, but you'll find tanks that don't have any sand in them. Of course, they don't have much pressure loss, but they're not doing much in the way of filtration. Find out what the backflush schedule is and the duration. Are they cleaning themselves out? You have to learn a little bit. You can find out about this stuff in our drip micro book. Moving on to a totally different irrigation method, grid type sprinklers. Now, what's that mean? It means that at one time or another, the grids are just the sprinklers are just stationary, and if you took a look at where they were over time, they would be in a grid. For example, hand move. There's a line of sprinklers. Here in California, it's typically every 30 feet there's a sprinkler. And then when you move it, which is once or twice a day, you move it 40, 45, 50 feet, something like that. And so basically you have a grid. When it's all said and done, a sprinkler has been on a 40, let's say a 30 by 50 foot grid. So they don't move while they irrigate. They rotate while you irrigate, but they are not moving. What's the biggest cause of non-uniformity? Usually the spacings are a little too wide. People move these things too far. Or with solid set, you have they're just too far apart. So what you see is you can barely see it in the upper picture. You can see the waving field of grain there. In other words, you'll see waves out there with showing the non-uniformity. It can be pretty obvious. One of the things you can do that's fairly straightforward if you have hand moving wheel lines is you move your pipes just regular as they're going across a field, but you make sure that when there's a pipeline, the next time a pipeline comes to that spot, it'll still move the same distance, but it's positioned midway between where the previous line was. So for example, if you're moving a line, you have a 50-foot move, you'll still have a 50-foot move, but you may position the subsequent line between the valves. So you have a little stub of pipe that goes out maybe 25 feet, goes from the valve over there and positions it. And what it does in effect over the course of 2 irrigations is give you half the spacing. You're putting on the same amount of water, you have the same duration, you have the same distance between lines, but over the course of 2 irrigations you have half the spacing, which really bounces the uniformity up tremendously. This next one is something that you can see easily from the air. It's not so easy to see from the ground, but you see all these circles here? That's what we call donut patterns. And Basically the guys are running sprinklers at too low a pressure, and so you don't get good uniformity. You see this in parks sometimes. It's a little more obvious in parks and golf courses, but in ag, sometimes you just have to get up in a little plane and see it. Sometimes it shows up on Google Earth. Now these three images here all show different types of filtration. Sure enough, when you have small nozzles, they can plug easily, or they can partially plug. So there are a whole variety of ways to filter out water that guys have come up with. And then the other one, it should be a no-brainer, but again, this is almost unreal. You go out to a stack of sprinklers in a farm yard, or you walk down a line and you look at the nozzle sizes, and I'll be darned if they're a mix. And sure enough, if you have big holes and little holes out there, you get big flows and little flows. It's this is not a tremendously complicated thing to solve. It just requires attention. Center pivots are a little different because with a center pivot, every sprinkler as you move outward from the pivot is a little larger, at least in concept, because each sprinkler as you move outward covers more area. It has a longer radius there. So well, you don't check nozzle sizes because you don't have, you usually don't have the printout and you know what the nozzle size is supposed to be. But what we do is put out cans, usually 2 lines of cans, big cans. You notice, make sure that they're all level. In other words, the tops are level, and you have the machine move over the cans, just regularly. And you should get the same amount of water in each can. Sprinklers are different sizes, but the machine moves at a different speed, depending on where you are out there. And all the cans should get the same amount of water in terms of milliliters, let's say. So that's what we look at. The reason we have 2 cans is these machines kind of jerk along sometimes. They don't just move steadily because of the way the electric motors are operated. They go in jumps. For pivots and linear moves, take a look at this picture and you'll understand 3 good things here. One is they have rotating sprinklers, and those have a lower instantaneous application rate on the soil than the old spray heads we used to use at the very beginning. Next thing, right above the sprinkler is a pressure regulator. There's a pressure regulator on every sprinkler, and that's good because that there's friction on the line. These machines go up and down hills, all that sort of stuff, and this maintains the desired target pressure at every sprinkler. And then the big white thing that's on the hose is a weight, and that keeps the sprinkler more or less hanging straight down from the machine, and it isn't blown around by the wind, and it helps give you a better uniformity. On pivots and linear moves, we also try to vary the rotation so that the machines aren't always in exactly the same place every time they rotate. And that's because you have wind patterns which do distort the wind can distort the overlap patterns, and wind patterns in most areas tend to be consistent. You have one type of wind, one speed, wind speed, and one direction of wind at 3 o'clock in the afternoon versus 7 a.m. in the morning. And so varying it a bit helps to smooth out these problems. And of course, filtration, as I mentioned before, filtration is the big one. It minimizes stand wear and nozzle plugging. That's a whole topic in itself. We don't really deal with that in the fertigation book. This is an aside here, but there are the horizontal filters like you have on the left-hand side. All you see on the upper right-hand side is some nasty stuff that made it to the sprinkler and the pressure regulator and landed on the spin plate there, which is obviously going to affect the uniformity. And then on the bottom right, you see what I call a mushroom screen. It's a little hard to tell, but it's used in the Rocky Mountain states for center pivots for a real simple type of screening device. And it's fine as long as you have some water that you can kind of just lose somewhere. Always have some water that's going through it that's not being used. Another thing about linear moves and pivots is um, that the overlap pattern does depend on how high the sprinkler is above the crop. And different sprinklers by different manufacturers with different nozzle sizes and different spin plates, trajectory plates, whatever you want to call them, will have different rules in terms of how high they ought to be positioned above the crop canopy. And certainly if you take the case like corn, which grows a lot over the course of the growing season, you would ideally start out with a lower sprinkler position than later on. And so you'll find some farmers actually have little hoops. They have arrangements. You can clamp the hose higher or lower, depending on what you want. But you have to have sufficiently close spacings, and you have to have the right distance above the crop. If you could imagine the extreme, if this was just right at the crop surface and the trajectory went downward, you wouldn't get much coverage at all. Surface irrigation is tough for a couple of reasons. Maybe the first reason is farmers who use surface irrigation have often done it, and their father did it, and their grandfather did it, and that's just the way it is, and they're not going to change too easily. But anyway, what are the basic rules? The first one is you have to have good land leveling, land planing. You have to have the smooth soil surface. It has to be at the right slope. Next is that there's no way that you can irrigate different soils in the same set at the same time and get the same amount of water in the ground, because the infiltration is basically controlled by the soil type. And then there's another one. This is a little more difficult to understand, and that's have no more than 50% difference in opportunity time between any points in the field. Now, the amount of time that water sits on the soil at one point versus the other is kind of equivalent to having different pressures at different sprinklers throughout a field. In other words, if you try to compare sprinklers and flood irrigation, with sprinklers we look at pressure differences. With surface irrigation we look at time differences. How long does the water sit at different places? With sprinklers we look at nozzle sizes. Do we have the same nozzle size everywhere? With surface we look at different soil types. Same kind of a deal. A sand is kind of equivalent to a big nozzle. More water goes in. So even though these look entirely different, the concepts are very similar. The left picture here shows you land planing. Land planing is not done with lasers or with GPS or anything like that. It's a machine with a blade in the middle, with a long distance on both ends of it, and basically with the number of passes over the field, it smooths things out. The picture on the right is a unit with it's very common that you see these. There's a tower on it, and that has a laser receptor on it, and that's for laser leveling. And that's what we call land grading, even though we say laser leveling. Obviously, they're not land grading that canal bank, but I just shot that picture when there was a tractor driving by. And with land grading, you actually sometimes you change the slope of the field. You maybe want a little steeper, a little flatter slope. Land planing is just really smoothing things out that already exist. But basically, you want the water to flow relatively evenly over the soil, and so you need both of these. This picture really has two things. One is clay loam is what you see here, but and you see the water stubbing up over to the sides. And in this particular picture, only every other furrow is being wet. And that's because the crop is still small, and with every other furrow, every crop row is getting water, but they don't need that much water, and so by irrigating every other furrow, you can have a good uniformity and not put on too much water. That's the idea. The problem comes in is if these furrows are clay loam and then you go down about 30 rows and it's sandy, there's just no way you have a uniform irrigation in the field. Also with sands, sandy soils, we need shorter runs than with heavier soil. Too much water goes in the ground just by getting the water from one end to the other on sands. So you can overcome that by having intermediate gated pipe or shorter furrows and shorter border strips. Now here's the one that really is a stumbling block for a lot of farmers, and I understand why it is, but this is just a fact of life. If you want to get about the same amount of water into the soil at different spots in the field, you need the equivalent of the same pressure. In other words, you need the same opportunity time. But here's what guys do. They will irrigate a field, they'll put water in at the top for 12 hours. It takes maybe 10 hours to get to the end, and they think they're saving water, see, because they don't have much runoff, or they can dam it up at the end. So they're saying, well, for what they can see, they're doing a good job. Now, this doesn't take a mental giant, though, to understand it if you think about it right. Let's see, if the water sits at the top for 12 hours and 3 hours at the bottom, is there any way that you'd be getting the same amount of water in the ground in 12 hours as 3 hours? And the answer is no, absolutely not. Unless you're in some odd place like the Imperial Valley, where they have cracking clay soils. And with cracking clay soils, you basically fill up the cracks and not much more water goes in. But most other soils that we have continue to infiltrate water as time progresses. Granted, at a lower rate over time, but they continue to infiltrate water. So let's see. If that doesn't work, in other words, and by the way, the reason people do that is they don't want to have tailwater. Well, what I'm saying is you really need to get the water down. If you irrigate for 12 hours, you should have gotten it to the end in about 6 hours. That's a 2-to-1, which means that it's running off for 6 hours, which means now you have to have a tailwater ditch, and you have to have a tailwater pond, and you have to have a pump to move the water back to the top. And suddenly that gets more complicated. There are a whole variety of ways you can design those. It takes land out of production, takes more thinking. It's a much harder sell. So far I've talked about distribution uniformity. Now I'm going to talk about irrigation efficiency. It's not the same. Here's the technical equation. It's the irrigation water that's beneficially used over the irrigation water applied. And beneficially used irrigation water really, most simplistically, it's water that goes for evapotranspiration. It also includes some water for salinity leaching and that sort of thing, but that's the idea. See, there's nothing in here about evenness. At least you don't see it at first. Now, see the times 100 on that equation? Irrigation efficiency is a percentage that goes from 0 to 100. Distribution uniformity is a fraction from 0 to 1. They are related, but they're different, and I'll try to show you how they're different and how they're related. Here's another little graphic that shows depth of water at different points across the field, depth of the plants. And this shows a really good uniformity. If you notice, the bottom of the deep percolation line is quite uniform. In other words, there's not much difference between one spot and another. Again, this has nothing to do with the specific irrigation method. The problem here is that the soil moisture requirement is considerably less than the amount of water that went in on the average, or everywhere. Everywhere there's more water that went in the ground than what was needed. That deep percolation then is water that you paid for that really isn't used. You might use it once a season to wash out salts, But the problem is when you do this all the time is you're also washing out your nitrates. On the other hand, this is where there's a misunderstanding of exactly what efficiency is. I hear this all the time. Well, I'm a great farmer, I'm a great irrigator. If I have a 2-inch deficit, 2-inch soil moisture deficit, I put on exactly 2 inches and man, I didn't waste a drop. False. What this picture shows is, let's see, average means that half the field has more and half the field has less, which means if you need 2 inches net, so dry your soil is, and you put 2 inches in on the average, that means half your field got more than 2 inches and half the field got less than 2 inches. So you have both under irrigation and over irrigation going on at the same time. Not at the same spots, but at different spots throughout a field. So what you try to do is you try to meet that soil moisture requirement as well as possible. In other words, you stop at the right time, but also you have a good uniformity. So yeah, is there deep percolation? Yeah, sure, but you try to minimize it. So what's the bottom line? If you want to have a uniform and efficient fertigation, you also have to have a uniform and efficient irrigation system and management. That's the bottom line. And that concludes video number 10 of our series from Cal Poly ITRC and the FREP from CDFA.